Hello everyone, I'm Meghamala from Electronics and Communication Department, working as an assistant professor in IARE, Dundigal. So far we have discussed about Verilog as an HDL, language constructs, and in the language construct we discussed about few lexical tokens. Okay, so coming to the lexical tokens, we discussed about comments, we discussed about the keywords, we discussed about the data types and so on. So coming to today's presentation, I'm going to talk about data flow modeling and continuous assignment and implicit assignment. So coming to the first slide, what is a data flow modeling? Okay, so here the data flow modeling is nothing but usually for small gate level modeling approach. It works well because we use less number of gates. That means the gates are limited and the designers can easily construct a digital circuits using gates individually. For each and every module using a limited number of gates, the designers they construct these circuits very easily. However, in complex designs also, the number of gates is very large. In the small designs, the number of gates would be very less, whereas in complex design, the number of gates are very large. So, in this case, the designers can design more effectively, and if they concentrate on implementing the function at a level of abstraction higher than a gate level. So, in this particular statement, it is talking about when we consider a complex designing. If we consider a complex designing, more number of gates are required. So if we are considering more number of gates, what happens is the network inside the gate looks very clumsy and it is very difficult for a designer to design in a very short time and in a very prominent way. So in order to overcome this, they are going forward for the data flow modeling. So the data flow modeling, it provides a powerful way to implement a design. So in order to overcome certain constraints, the designers are going for the data flow modeling, where it provides a easy way, a powerful way to implement a design. When it comes to a designing of a circuit, and it is very easy to design a complex module. Okay, it is very easy to design a complex module using data flow modeling. And also, Verilog allows a circuit to be designed in terms of data flow between registers and how design process data rather than instantiation of individual gates. So this very particular statements, it is talking about the Verilog circuit to be designed in terms of data flow. The data flow, in terms of data flow, the design of the electronic devices would be encouraged because the data flow between the registers are easy to be carried out, and also the design process of data rather than the instantiation of individual gate. So instead of considering each and every particular gate, it is always going ahead. It is always thinking ahead is more important. So in this way, particularly thinking about each and every individual gate, the process of each and every individual gate, it is much more time taking. So in order to avoid that, the data flow modeling is helping us out in order to design a complex electronic circuits. So the data flow between the registers is carried out very easily when it compared with each and every individual gate, considering each and every individual gate and the communication between these two gates. Okay, this is about the data flow modeling. Going ahead. Next, the automated tools are used to create gate level circuit from data flow design description, and this is called the synthesis. In the previous presentations, we have discussed what is synthesis, what is simulation, what is a module concept and all, isn't it? In the previous one, Verilog acts as an HDL. In that particular topic, we discussed what is synthesis, what is simulation, how a Verilog program synthesizes and it simulates to get the output. So this here, in order to synthesize a particular program using a data flow level modeling, the automated tools are used to create a gate level circuit. Okay, the tools that create a gate level circuits in order to flow the data between the registers, between the two components. And this is nothing but the logic synthesis. Okay, this is nothing but the logic synthesis. And for maximum flexibility in the designing process, for an easy way, for maintenance of easy way, they typically use Verilog description style. So for the flexibility, in order to achieve the maximum flexibility, the designers are using a Verilog description style. This combines, or else it has, the concept of gate level, data flow and behavioral design. So these three are the very important topics, very important things which we can observe in the Verilog in order to run a program in a very specified manner. So by using these three, the designer can achieve the maximum flexibility. That means what he can achieve, or else he can know whether the errors, he can find out whether the errors are present in each and every block, in the module. So already we have discussed about what is gate level, what is data flow, and what is behavioral design. And also we have discussed about the syntaxes pertaining with these three levels. Okay, so in the behavioral level, we use a keyword called always block, and in the data flow, we use a keyword called assign, and in the gate level, we are using simply we are deriving, or else we are the syntax is very simple based on the particular gate that you are considering. Using gate in the gate level, maximum possibility is we are considering the prominent gates like AND gate, NOR gate, AND gate, XOR gate, and all, etc. So the maximum flexibility can be achieved by using all these three designs. And also here you see a word called RTL. What does this RTL means? RTL is a register transfer language. So what does it mean? What does it mean is it is commonly used for the combinational of data flow modeling and behavioral modeling. See, if you observe this word RTL, it says that the data between the registers can be carried out easily, and especially this RTL we see in the combination of data flow modeling and as well as in behavioral modeling. Okay, coming to the continuous assignment. What does this continuous assignment talks about? It says that it is the most basic statement in data flow. As we are discussing, the topic for today is data flow modeling. We will see how the syntax, or else how the program can be written in the form of continuous assignment. So this continuous assignment, it is the most basic statement in the data flow modeling. It used to drive a value onto a net. So in the yesterday's previous presentation, we have discussed what is net, what is block, okay, what are the delays, and what are the scalar and the vector values, components. So net is nothing but it is a combination, or it's a group of individual bits. It's a group of individual bits in the module. For example, if you consider a module, this is if for example it is a complex module. If it is a complex module, this complex module consists of numerous blocks inside. The blocks are constructed inside the module. You see many, not one, but more than two. We see the blocks, block 1 and block 2. So each and individual block, it signifies its own specification. It has its own specification and it generates some output. And that output indeed there is a connection between the simultaneous blocks. So this cluster is nothing but a net. So here it says that a continuous assignment, it is a most basic assignment statement in the data flow modeling. This used to drive a value onto a net. So each and every block, it has some value. The value is specified for each and every block, though it may be input value, though it may be output value. So it is all about this assignment, continuous assignment, it assigns some value onto a particular net. Next, this assignment replaces gates in the description of the circuit and describes the circuit at higher level of abstraction. So this particular assignment, this continuous assignment, what it does, it replaces the gates in the description of circuit. So in the description of circuit, for example, if you're considering any digital circuit, that circuit is made up of any kind of gates. It just replaces the gates in that particular circuit description, and in order to achieve the higher level of abstraction, or else in order to achieve rather than gates, we can go for the data flow modeling. So this assignment, continuous assignment, it can replace the gates in order to achieve the data flow modeling. In order to make the process very easily, this assignment, continuous assignment statement can be replaceable with the gates. And coming to the third point, the assignment statements, it starts with the keyword assign. So the syntax of assign statement is as follows. So this particular assignment statement, in order to write in the syntax, particular syntax, it starts with the keyword assign. Keyword is one of the lexical tokens, one of the language constructs. In the previous classes, we have discussed what are the language constructs. We have different language constructs. Coming to the language element keyword, we discussed about few keywords, right? Module, end module, if, while, begin, and end. So these are the few keywords where these keywords are used. They have some specification. The significance of this module, it represents the starting of the program, starting of the syntax, starting of the digital circuits that you are considering, whatever it is. For example, coming to the module, we have discussed module and gate. Okay, module and gate. And coming to the end module is nothing but it is a termination of the syntax. Finally, at the last, we mention end module. And what is begin and end? Begin and end are nothing but inside the block. Inside the block, this block has few statements, and these statements, the beginning of the statements, the begin is a keyword where it indicates the beginning of the statements inside the block. Okay. And end is nothing but the termination of that particular block. We are ending up with a keyword called end. And coming to the if and while, these are the conditional statements. Okay. And these conditional statements, if and while statements, are nothing but we can see, as I said you, Verilog is a very case sensitive language, and it can also be related to the C language, normal C language. So this if and while are also be used as a keyword in different conditions, in different areas in the Verilog. So coming to this continuous assignment, it starts with a assign keyword called assign, and the syntax follows like this. So the syntax goes here, continuous underscore assign. We are assigning some drive strength with a delay of 3. And next, coming to the list of net assignments. And here we have few assignments, and that assignments in the form of list. Okay, in the form of net. So the list of net assignments. Next, list of net assignments are nothing but the net assignments, net underscore assignments. Okay, these are again individually we have to segregate into the, in the flower basis, we have to segregate them. What are the net assignment states? Next, net assignments, indeed it consists of the net values and the expression. Okay, so this is all about the continuous assignment statement, and this is about the syntax that we are using. Remember that continuous assignment statement can start, it starts with the word called keyword assign. Coming to the characteristics. What sort of characteristics that does this data flow modeling has? So this data flow modeling, it has the left hand side of assignment must always be a scalar or vector net, or a concatenation of scalar and vector nets. So what does this left hand side and right hand side indicates? So in the particular statements in the previous slide, we have discussed the syntax, right? So in the syntax, we see the left hand side of the assignment levels. There always it should have always a scalar or a vector or else a concatenation of scalar and the vector nets. So what is this scalar and what is this vector? In the previous presentation, we have learned what are the scalar net and what is vector nets. So what are the scalar nets? Scalar nets are nothing but the individual bits. Okay, these are the individual bits. For example, I'm considering circuit 1 and I'm considering circuit 2. So this circuit 1 and this circuit 2, the processor easily it can read the data and also it can write the data. So individually they read the bits which the circuit 1 can read from circuit 2, and the write operation can also be performed with respect to circuit 1 and the circuit 2. These are the individual bits consist of very few little bits or very few bits. It could be either 1 or 2. So the individual bits we are calling it as a scalar net, and the group of bits. For example, here we have D0 and D1, D2 and D3. Okay, the bits where we can achieve, we can assign in the circuit 1 and that can be transferred to circuit 2 is nothing but D of 3:0. That means here the number of bits in this particular register, the number of bits we have is 4 bits. Register contains 4 bits. How? 3, 2, 1 and 0. These are nothing but the vectors. And these are nothing but the scalars. Okay. So, as per this, the characteristics states that the left hand side of the assignment values, they may have always a scalar net or else a vector net or else both, the concatenation of both the scalar and the vector nets. It cannot be a scalar or vector register. Register kind of things we won't see anywhere in this particular continuous assignment, but we see only either a scalar or vector or else a combination of both, the concatenation of both scalar and the vector nets. Coming to the second point, continuous assignments are always active. So these assignments are always active because the assignment expression is evaluated as soon as one of the right hand side operands changes a value is assigned to the left hand side net. Why? Because here you will see the assigning of the bits. Right hand side operands, they changes and the value is assigned to the left hand side. You see the assignments for the right hand side for LHS, RHS and the LHS, you see the assigning the value. If you are assigning the value at the right hand side some value, it may change. And it may change and it may given to the left hand side. So this statement is talking about whether like you are changing the values from RHS to LHS and from LHS to RHS. So such that we are calling it as these assignments are always inactive. Next, the operands on the right hand side can be registers or nets or functional calls. Registers or nets can be scalar or vector. We are calling it as the operands on the right hand side. The right hand side operands can be A, B, C and so on. So these operands can be of registers, nets or function calls. What are these registers? It means that the right hand side, whatever the values which are present in the right hand side of the continuous assignment statements, they can be registers. Register is nothing but a group of digits. Group of digits which are accumulated in one particular place called registers. So registers are nothing but the combination of flip-flops and latches as we know in the digital circuits, isn't it? Nets are nothing but the combination of blocks, one or two more and blocks, the communication between one or two more blocks, more than 2 blocks, we are calling it as a nets or function calls. So the right hand side, the operands which are present at the right hand side of the continuous assignment, they can be in the register or else in the net or else in the functional calls. So the registers or nets, as we discussed, they can be scalar or vector. They can be individual group or else they can be a group of bits together in the register. Next, delay values can be specified for assignments in terms of time units. We see in the previous syntax, we have seen the continuous system, the continuous assignment, it was assigned with a delay 3. With a delay 3:0. What does this delay means? Always remember the delay are the terms in terms of time units. Okay, here the delay is of 4-bit delay. Okay, the clock pulse, it takes 4 clock cycles, so it is of 4-bit delay. So the delay values, they can specified in the assignment statements in terms of time units. This is very easy to remember. Next, delay values are used to control. They control the time when the net is assigned the evaluated value. So when the net is assigned for the evaluated value, that means when you see an increment in the each and every block inside the network, you see the delays can be specified. That means what? For each and every individual block to obtain the output, the individual block has to go through some delay. We will observe some delay. So that delays, they are used to control the time when the nets are assigned to the evaluated value. When the value is incremented, then the delays are used to control it. Next, this feature is similar to the Verilog, similar to the specifying delays for gates. So obviously in the gates, for the processing of information between the registers or else between the blocks, we see some delays to be occurred. So this is a similar feature. This is a common feature that we observe, and it is very useful in modeling time behavior in real circuits. So you will observe. This is easily can be observed in the time behavioral in the real circuits. In the real circuits, the delaying process can be achieved, and we can observe very easily. Coming to the examples of continuous assignments. So here are the few examples. This continuous assignment, continuous assign is a keyword. So it has out is a net. Okay, net has some output, and I1 and I2 are the net's input. Assign out I1 and I2. So here we have two inputs, I1 and I2, and we have output. So as we have discussed earlier, the continuous assignment, it starts with a keyword called assign. So assigning net out as two inputs, I1 and I2. Very clear. Next, continuous assigns for vector nets. Address is 16-bit vector net. So here for this continuous assign for vector nets, for this vector nets, how much of bits that we are considering is, it is a 16-bit vector net. As I said you, vector is nothing but the group of bits together. Okay, so in this vector is nothing but if a register, more than one register, R1, R2, R3. So each and individual register will have some bits. 3:0, 5:0, and 7:0. So these are nothing but the bits which are grouped into individual registers, and so we call it as a vector. So the continuous assign for the vector address is 16-bit vector net. Next, address 1 and address 2 are 16-bit vector registers. So two registers they are considering, address 1 and address 2, and this assign address 15:0. Okay, so here it is as a 16-bit. So how we are dividing? 15:0. That means 15 plus 0, 15 and 1, 0. It is totally 16-bit. So address 1 bits of 15:0 and address 2 bits of 15:1. Here, and using AND operation, we are concatenating the two vectors. Okay, the continuous assignment previously stated that it could be either scalar or it could be either vector, or else it must be the concatenation of both vector and as well as the scalar. So here we are concatenating both the address bits, address 1 and address 2. So the concatenation, left hand side is a concatenation of a scalar. So as here it is, this is a concatenation of scalar, whereas it is a concatenation of two both vectors and a vector net. So here assign, so using the syntax for in the continuous assignment, the syntax goes like this here. Assign, flower braces, C is the output, and the sum is 3:0. Okay, totally 4-bit we are considering, sum is 3:0. Therefore, A 3 is to be 3, A of 4 bits, B of 4 bits, and C. So you can consider this as a for full adder. For full adder, you see input, output, and Cin. We can have the 3 inputs with the output, and the sum goes when you add, the sum goes S1, and the carry bit goes as a C1. Likewise, if you consider the 3 full adders, adder 1, adder 2, adder 3, the input output bit summed as S1, S2, and the output carry bit summed as C1 and C2, and so on. Okay, this is example for the continuous assignment. Coming to the implicit continuous assignment. What does this implicit continuous assignment means? Instead of declaring a net and then writing continuous assignment onto the net, Verilog provides a shortcut with the continuous assignment can be replaced with the net when it is declared. So each and everything this is in the continuous assignment, we are simply using a keyword assign along with the net, and this net consists of some vector and the scalar bits, isn't it? So instead of declaring a net, what it is declaring, it is usually declared a keyword called wire. So here there can be only one implicit declaration, continuous assignment declaration, in contrast with regular. What is that one continuous declaration is wire. So if you observe these two, regular continuous assignment, we wire out, assign out, in and out. Okay, the same is achieved with the implicit continuous with wire out, in one and in two. So here if you observe, in this implicit continuous assignment, you won't see any keyword called assign, whereas in regular continuous assignment, we see a wire out along with the assign. Assign is a basic keyword in order to implement this continuous assignment statements, right? So this implicit is something different, which is you will not assign a keyword called assign. Simply you will write the wire out individual bits, individual inputs in one and in two. Here in the normal continuous assignment, you see assign out, but whereas here in implicit continuous assignment, you won't see any assign out. You see only the wire out. Wire out is nothing but it is a one bit of output representation where that output acts as an input to the next gate. That is, in the previous example we have discussed, this is A and B are the inputs, C is the output, and that output we are wiring it with this wire. The output again acts as an input to the next individual gate. Okay, so this is only meant for only one bit of data. So in the implicit continuous assignment, no assign keyword is mentioned, simply wire out for in one and in two. That is, in one, and if this is in one and if it is in two, the wire out would be this one, output. This is nothing but the implicit continuous assignment. And coming to implicit net declaration. What does this net declaration states that? It says that if a signal name is used to the left of the continuous assignment, implicit net declaration will be inferred for that signal name. So whatever the signal name, whatever the name that you are indicating to the left hand of the continuous assignment statement, that name itself is nothing but the net declaration of that particular signal name. The net declaration would be assigned, or else it will be considered for the whatever the name that you are indicating to the left of the continuous assignment statement. So if the net is connected to a module port, the width of the inferred net is equal to the width of the module port. So here, for example, this sentence is talking about if a net is connected to module port. This is a module. We have input ports, entry bits, and this is the output port, exit bits, and it has in-out ports. So here, if the net is connected to the module port, so this module port has some net, some registers R1 and R2. Okay, the width of that inferred net is equals to the width of the module port. So how much of length this net consists of? If this length is, then if this particular net length is 2. So the same net is the same width, the same width will be occupied inside the module with the same 2. If the length bit of the net is 5, the same would be occupied in the module with the 5. If it is 10, the same would be occupied with the module 10 and so on. So the net is connected to the module port, whereas it has the same width, equal width of the module port. So here we have wire I1 and I2. So assign out, the output is nothing but I1 and I2. I1 and I2 are the inputs. Out is the output. Assign is a keyword. So the statement states that note that out was not declared as wire. So here you observe in this implicit net declaration, we are not declaring the output with wire, isn't it? But in the previous implicit continuous assignment declaration, we are declaring in the implicit continuous assignment a keyword called wire. But whereas here in implicit net declaration, in the net declaration, wire is not meant to declare. Simply assign output which is equals to both the inputs. Concatenation I1 and I2 is sufficient. But an implicit wire declaration for out is done for the simulator. But in the Verilog simulator, if it is needed, automatically it can change. That means the keyword wire can be changed to the output, or else the output can change to the net. Okay, in the simulator, automatically the changes can be seen inside the simulator. So coming to the delays. What are the delays? Delays are nothing but they control the time between the change in right hand side operand and when new value assigned to the left hand side. So if you have assignment statement, with a net list, this is LH, this is RHS, and this is LHS. LHS has some scalar quantity, and if it has some vector quantity, what does it say is the delay control the time between the changes in the RHS, operand when the new value is assigned to the left hand side. If for suppose this continuous assignment statement, it has some the data 5:0. Okay, so the output we observe would be 25:0. What happens sometimes? Some errors may occur. So in order to avoid that errors, or else in order to rectify that errors, what happens? Some values can be inferred. So that values can be inferred to the LHS of the left hand side of the continuous assignment statement. So when we are inferring some values to the left hand side assignment statements, what happens? The delay is occurred, right? So the delay is nothing but the control, the timing control. The delay we may see maximum delay, or else we may see the minimum delay. But the delays occurs when the values changes from the right hand side to the left hand side of the continuous assignment statements, the values. Next, the 3 ways of specifying delays in continuous assignment statement. So there are 3 ways to specify the delays. They are regular assignment delay, implicit continuous assignment delay, and net declaration delay. So the 3 delays that we can observe here is regular assignment delay, regular one, implicit continuous, and net declaration. Already we have discussed in the earlier, but in terms of delay, we will see what are those. So regular assignment delay, it is nothing but the delay is specified after the keyword assigned. So here, after assigning the keyword, so keyword assign, we see the delay 3:0. So here we see the delay value is specified after the keyword assigned. Only after assigning the keyword we have to indicate, or else we have to specify this particular delay. Next, any change in the value of input 1 or input 2 results in delay of 10 units before the recomputation of the expressions 1 and 2, and the result will be assigned to odd. Obviously, if for suppose my input 1 is the processing of input 1 would be in 10 nanoseconds. The processing of input 2 would be in 20 nanoseconds. So the difference here you see is 10 nanosecond difference is observed. But when we observe at the output, that means what? The concatenation of both inputs 1 and 2, 10 plus 20, we need to observe the 30 nanoseconds. But in the process, what happens due to some impairings, we see instead of 30 nanoseconds, we see only 29 nanoseconds. So here we are missing 1 nanoseconds of delay we are observing. So any changes in the input 1 and or input 2, they could be in the delay, it would be in the 10 time units before the computation that we observe in the coming diagram. So if input 1 or input 2 changes value again before 10 minutes, then the results propagates to output and the values of in1 and in2 are to be considered. So see, this is a figure pertaining to the delays. Here my input 1 is, I'm observing input 1 and input 2, and this is the output with the time mentioned 10 nanoseconds, 2, 30, 40 and so on. So this is generated by simulating the above statement, by simulating the above assignment statement. So it shows the delays on signal node, signal out. So say here, in one, see, assign keyword is assigned. We are denoting a delay of 10, which is equals to input and as well as the output, and delay in a continuous assignment. So here as a word assign, it's a continuous assignment statement. In the continuous assignment statement, a keyword called delay assign is used, right? So this is nothing but delay in continuous assign. So here it says that delay input at 20 nanoseconds and output, both the inputs are at the 20 nanoseconds. The output time, it indicates my output is going at the 30 nanoseconds, isn't it? This is what we have observed here. See, when the signal 1 and signal 2 high at 20 nanoseconds, it goes after 10 times unit later, isn't it? So in 1 and in 2 are going at 10 nanoseconds difference, 20 nanoseconds, but my output is going with a delay of 10 nanoseconds. So the input 1 changes at 80, it goes before 10 minutes, and see, so my input value, it again processed, it's coming down at 60 nanosecond, and again it's taking a break and at the 80 nanosecond with a 10 minutes of delay. Here 10 nanoseconds of delay, my input value is going out. So whereas for input 2, the output is constant. Okay, the output is going as constant. So but when we can concatenate both input and output, we see with the 10 minutes of 10 nanoseconds of delay, we are observing the output at 10 nanoseconds of delay with both input 1 and input 2. We see 10 nanoseconds of delay at the output. So whatever, with how much of delay at the input we observe, the same amount of delay that can be observed in the output also. Coming to the implicit continuous assignment delay. What does this implicit continuous assignment be? In the previous slide, we have discussed implicit net declaration, whereas here implicit continuous assignment delay. It is an equivalent method to use implicit continuous assignment to specify both a delay and a assignment on the net. So in order to specify both delay and assignment on the net, we are going for this implicit continuous assignment delay. So how it goes is implicit continuous assignment delay. Wire is a keyword which is assigned. 10 out, 10 is nothing but the delay with delay of 10, and the output is equals to in1 and in2. These are the inputs. So same as wire out. Okay, this is in terms of implicit continuous delay, whereas this is simply a implicit continuous assignment. So here in this implicit continuous assignment, we use a keyword called assign with a delay 10 out, n1 and n2, but we are using a keyword saying that wire out. So the declaration above has same effect as defining a wire out and declaring a continuous assignment on out. So wire out and assign out, both are same, declared with a delay 10. Okay, with a delay 10. Coming to net declaration delay. What does this net declaration delay specifies? It is a delay. It can specify on a net. It's a net declaration, right? So it can be specified on net without putting a continuous assignment on the net. So not just considering the continuous assignment on net. It is just specifying a net on the declaration part. The delay declaration would be only in terms of net, but not in the continuous assignment on the net. So if a delay is specified on a net, in the net, if delay is specified, then any value change applied to the net out is delayed accordingly. So it is very simple, right? If some delay is observed in net, so if some delay is observed in block 1, and the same delay we will see in the block 2. Why? Because there is a communication between block 1 and block 2. The delay, if it is occurring in block 1 at 10 nanosecond, the same will be carried out to block 2 with the same 10 nanoseconds. So if a delay is specified on a net, then any value changes and it is carried out as delay accordingly. Next, net declaration delays also be used in gate level modeling. So not only in the data flow modeling, but also we see the net declaration delays. The net declaration delays can be observed in the gate level modeling. So here goes the syntax. Net delays, net declaration delays. So net delays, via is a keyword assign, and 10 is a delay out. Assign is a keyword out, which is an input 1 and input 2. The above statement has same effect as the following. So the following statements, if we compare these two statements, the above one and the below one, we see wire out. Here we are declaring with the delays. Why? The difference between these two is net declaration assignment. In the net declaration assignment, we don't declare any word delay. But whereas in net declaration delays, we are representing or else declaring as 10. 10 is nothing but the delay. That means 10 nanoseconds of delay is been declared. Whereas in the normal statement, if you observe, wire out, assign 10 nanosecond out, that is int 1 and int 2. Okay, so this is a difference, a small difference between the declaration continuous assignment and continuous assignment statement and the net declaration delay statement. So this is what about today's presentation. It's all about the data flow modeling, continuous assignment statements. Different continuous assignment statements we have discussed based on the delays, based on the nets. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.